and with great pleasure introduce Alex Fink, coming to us from Queen Mary University. Go ahead, Alex.
Thanks, Graham. Okay. Share screen on, and there we go. Slide visible. Right. So thanks everyone for coming. Thanks in particular to those of you who have given up your Stanley birthday conference lunch for another talk or whatever it is at the Sotilli birthday conference. So this is a talk on some work in progress with Andy Berget, a paper we're writing in which we prove David Speyer's G conjecture arising from consideration of face vectors of tropical linear spaces. So outlining that is the goal of my talk today, and I will start with just reviewing the perspective on matroids that I like to take for these things. So this is a lesser used as a definition of matroid, but it's when I like to say that a matroid is a certain kind of 0-1 lattice polytope, namely a type A permutahedron among those. So it should be a polytope. The ground set is 1 through n, say, oops, that's not the highlighter. The ground set is 1 through n, say. So then it's a polytope that lives in Rn, with vertices being 0-1 vectors, and all edges parallel to some difference of 2 standard basis vectors, ei minus ej. So here I have, for n equals 4, actually all of these polytopes always lie in a hyperplane, because all the possible edge directions lie in a hyperplane. So I've drawn 2 of these polytopes for n equals 4 in R3, and you can see that the one on the right has this edge where 2 coordinates go from 1 to 0 and 2 coordinates go from 0 to 1. That's not parallel to one of these directions. That's not a matroid. The polytope on the left has no such bad edge, so it is a matroid. Another example is if I take the convex hull of all the 0-1 vectors whose entries have a certain sum, some integer r, between 0 and n inclusive, I get the hypersimplex, which in this language for matroids is the uniform matroid denoted URN. So in terms of a more familiar matroid axiom system, what we're doing is encoding the bases of a matroid as 0-1 vectors, and then taking their convex hull. When you do this, the exchange axiom, after a little bit of work, translates into this condition on the edge directions, but you can at least see that if the vertices corresponding to bases are linked by an edge in this direction, then the bases are related by an exchange where I put in element I and drop element j. And the rank of the matroid is the size of any basis, so the coordinate sum for any point in the polytope. One more bit of initial matroid review. I'll do more matroid review as it comes up, but my last bit of initial matroid review is representable matroids. We'll set it up starting with a linear space of a vector space over a field with a prescribed basis, so I may as well call that k to the n, where k is my field. Given this, I get a matroid. There's various ways to describe the process, but you can think of taking a matrix whose row space is my prescribed linear space, that's of full rank. So if L is r-dimensional, I want an r by n matrix, and then I look at its maximal minors, and the non-zero ones give me the bases of my matroid. So this is probably review for this audience. In the last 15-ish years, there's been a lot of interest, maybe more, there's been a lot of interest in matroid subdivisions and matroid valuations. For instance, they showed up in Kapranov's work on Lie complexes, Hackett-Gill and Tevelev, lots of appearances in tropical geometry, I guess before this in Laforgue's fields metal work. And these valuations have been recurrent in the matroid Hodge theory program. Functions that are linear on matroid Chow rings turn out to be valuations in this sense. So these are hot notions in matroid theory these days. What's a matroid subdivision? It's a cell complex where I take a matroid, which is a polytope, and I cut it up into smaller matroids. So my example here is the uniform matroid U24. That's the octahedron, this hypersimplex. Well, if I cut it through this gray plane in the middle, that cut doesn't introduce any new edges, so every face of the subdivision that's created is still a matroid. The maximal faces are this square pyramid up here on top, and this square pyramid down here on the bottom. And then there are various other faces as well. Given one of these, you can look at functions which are, add in the way a measure. So those things we call valuations. So they satisfy an inclusion-exclusion relation, namely that if I've got a matroid subdivision, the matroid I'm subdividing is called M. The maximal cells are M1 through MK. Then I want to be able to write M as so in this case, this is M1. Write a bit bigger. This is M2. The maximal cells are M1 through MK. I look at all of their intersections of all subsets. So in this case, M1 intersect M2 is the gray square I've denoted M1, 2. I take an alternating sum of the values of f on these pieces, and if that gives me f of the whole, that is the inclusion-exclusion relation that defines a valuation. So concretely here, f of the octahedron has to be f of the top square pyramid plus f of the bottom square pyramid minus f of the gray square. For David Speyer's g-invariant, it's convenient to twist the signs on this, right? There were alternating signs in the previous equation, and I just want to get rid of them. The way to do this from the measure-ish point of view is to think of open cells of the subdivision instead of closed cells. So the interior of my polytope is just partitioned into other interiors of polytopes by the subdivision. And if I add up functions, thinking of them as accounting for the interiors of the polytopes, I just get a sum with no signs. So I can rewrite the summation that way. And I'll call such a function a matroid co-valuation. So that's just a matroid valuation with the signs made all positive. F of the whole octahedron is f of the top square pyramid plus f of the bottom square pyramid plus the square. Okay. So the question that led David to introduce his g-invariant, which is the polynomial invariant of a matroid that's the subject of this talk, is to bound the number of cells you can have in a matroid subdivision in the f-vector way, where you care about how many cells of each dimension there are. The largest matroid polytope is the uniform, so getting a bound for that is a place to start. So one case of this, which appeared in this paper of Speyer, using the beta invariant of Crapo that appeared in the literature before, gave you the answer for maximal cells. Since we've seen that all matroid polytopes lie in a hyperplane, the largest dimension a matroid can have on n elements is n-1. That's the case when the matroid is connected. And so if we want to count the n-1 cells, this beta invariant is a classical function of a matroid. It's a coefficient of the top polynomial, the x coefficient or the y coefficient. If the thing has more than one element, they're the same. And it has the properties you need to give a bound on this. Namely, it's always non-negative. It is a co-valuation. It's both a valuation and a co-valuation, in fact, because it is 0 on all disconnected matroids and strictly positive on all connected matroids. That's when I should have highlighted this. Meaning that if I want to evaluate beta of my big M, say, URN, well, I get a positive contribution from every maximal cell and a 0 contribution from all the lower dimensional cells. A positive natural number is at least 1, so I get at least 1 contribution from all the maximal cells, but the total sum is beta of m. So beta of m is an upper bound on how many things I was summing up, so beta of m is an upper bound on the number of cells. So in particular, beta of the uniform matroid is this binomial coefficient. So that's the upper bound for the number of cells in this subdivision of URN. And in fact, it's achieved. There's a nice subdivision into lattice path matroids for ribbons, which achieves this. Okay, so to do some argument like that in general, maybe one way you could set it up is to say, oh, we'll have a polynomial, and the degree of the indeterminate t in the polynomial will do the argument like this for the cells of that dimension, right? So this polynomial will be a polynomial encoding of the f vector, a polynomial bound on the f vector. And if you replace dimension with codimension, and look at not the degree, but the least exponent, this is the game that David Speyer's G is playing. So David was able to prove that there is this polynomial G that is a polynomial with integer coefficients. It is covaluative. And when I evaluate it on a matroid with, say, k connected components, that's the codimension of m, then the G polynomial will be something times t to the k plus higher order terms. So this means you can look at the coefficient of t to the k to bound the number of cells of dimension k, as long as you have the remaining property that the coefficients are non-negative for the inequalities to go through. So David was able to prove that in characteristic 0, but not in general, let alone for unrepresentable matroids, and so left that open as a conjecture. Maybe it's worth noting that David's proof in characteristic 0 used cumulative Fivek vanishing of a vector bundle here, which is genuinely a characteristic 0 fact. The corresponding vanishing for vector bundle in characteristic P is not true, and so maybe this is one hint that, the matroid Hodge theory isn't quite what's going on here, because that's characteristic independent. So there is some interesting geometry going on here. David conjectured with, plenty of evidence beside these representable cases that actually this g-invariant had non-negative coefficients regardless of the matroid. So in a piece of work which shamefully we did at, maybe this should say something like 2016 plus, David and Chris Shaw and I did at the Fields Institute in 2016 and then didn't write down. We reduced David's conjecture for the whole polynomial g-invariant just to looking at its top coefficient, which we've called omega. In fact, right, in general, g of m, oops, let's switch to pen, g of m for a typical m, this is not my usual tablet, not quite used to it. G of m is 0 plus beta of m times t plus something. And then, okay, so if you think you're assigning the Greek alphabet, the alpha term is the 0th order term, the beta term is the 1st order term, t to the 1. At the other end is the other end of the Greek alphabet, omega of m times t to the rank. So that's what explains our choice of omega. Anyway, we reduce this conjecture to showing that if you can prove the top coefficient positive for all matroids, you can prove the whole conjecture for all matroids. This is via localization style intersection theory computation. You look at the Bergman fan, the corresponding cohomology class in the permutohedral variety. You want to, Chris Shaw has a formula for omega, or for G rather, you evaluate that locally on a face of the Bergman fan, and the thing, it turns out, breaks up into a product of sums of G and known positive things. So that's from 2016. We should finish that paper soon. And given that, Andy and I have proven recently that, in fact, this top coefficient is non-negative for all matroids, which implies that all the coefficients of G are negative for all matroids. So at this point, I should define David's g-invariant. It is, the definition is algebrogeometric, but if you want to compute it by hand, it might be easier to do combinatorially using the properties on this slide than algebrogeometrically, so I'll run through those first. So proposition by Speyer, there exists a polynomial function of matroids, which has the three properties on this slide. If I take uniform 1, 2, I send that to T, the invariant. If I have a matroid, I take a series or a parallel extension. That doesn't change the g-invariant. So in particular, any series parallel matroid, which I get by doing iterated series parallel extensions on U1, 2, the g-invariant of such a thing is still T. And finally, it should be multiplicative under direct sums. So especially if you can subdivide a matroid into series parallel pieces, this lets you compute G, which is what I've done in the example at the bottom with the square pyramid. This is the subdivision from before, and it turns out the two square pyramids are series parallel. Each of them contribute a T. The square is U1, 2 direct sum U1, 2, so that contributes a T squared. G is co-valuative, so I just add up all those pieces, and I get 2t plus t squared. That is the evaluation of this thing for U2 form. All right. On to the algebrogeometric definition. David gave a definition using a torus orbit in the Grassmannian. It's nice to reinterpret this in terms of the permutahedral toric variety, but we'll start in the Grassmannian. So if I have a representable matroid, it's represented by a linear space. That gives me a point in the corresponding Grassmannian. I also have the torus action. I'm working over the complex numbers here, so the torus C star to the n acts on C to the n just by scaling coordinates of by scaling coordinates. So it acts on the set of subspaces of C to the n, which the Grassmannian is the parameter space for. So I get this torus action. I can take the orbit of my representation, take its closure. The closure of a torus orbit is a toric variety, and it turns out it is the toric variety of the matroid associated with the matroid polytope. Now that's nice, but as I said, I'd like to work, not on all of these different toric varieties, but in one toric variety. So since every matroid is a generalized permutahedron, that is, its normal fan is a coarsening of the normal fan of the permutahedron, which is the braid fan. This implies that the toric variety of the permutahedron is some iterated blowup of the, or not necessarily an iterated blowup, but at least has a surjective map to the toric variety of the matroid polytope itself, which is this orbit closure up here. So using that, we can pull back the geometry that David and I did in this setting into the permutahedral variety. For sign convention reasons, we'll actually do it as I did here on the bottom, and twist by the Cremona map of the permutahedron, invert all the coordinates of the torus, just a sign convention. So we've got that map. And now we have tautological vector bundles on the Grassmannian, the tautological subbundle and the quotient bundle, whose fiber over linear space are that space and the quotient of the ambient space by it. These are standard constructions, and the star of this paper of Berget, Eur Spink and Tseng, published last year, are matroidal versions of this, in the sense that if I have a linear space, I can take these bundles and pull them back across the map pi L and get two bundles on the permutahedral variety Xn called SL and QL down here. Now, if I have a matroid without a linear space necessarily associated, well, what can I do? I can look at the classes of these bundles in torus equivariant K theory of the permutahedral variety. It turns out that this association is valuative, or at least extends to a valuative function defined on all matroids. So I have an element of this torus equivariant K ring defined for every matroid called S sub M, and an element called Q sub M that agree with S sub L and Q sub L in the case that M is representable. And so these are not quite vector bundles. They are just, the information in the K theory class of the vector bundle, which is reasonably combinatorially rich information about the matroid, but it is purely combinatorial. If you do equivariant localization, you see that the data you need to build these things is just take every order of the ground set, record what the lexicographically first basis of your matroid is, and it turns out that gives you a class that you can, or the data to assemble into these K-theory classes. So we don't have vector bundles, or at least we don't have vector bundles with the positivity properties that we'd like. You can cook up some kind of vector bundle with these classes, but we work with the classes. Matroids have vector bundles on the permutahedral. Sorry, representable matroids have vector bundles on the permutahedral. Any matroid has a K class of such a thing. So here's the definition of G. Cast in the arbitrary matroid language, coefficient-wise, to get a coefficient, you take a wedge power of S, tensor it with the same wedge power of the dual of the quotient subbundle Q, and you take the Euler characteristic of this thing. You can actually evaluate this Euler characteristic by push forward to a point in K theory, and so you can do this purely on K classes, and that's why this is a meaningful expression. It doesn't need to have a literal vector bundle to do this thing. David and I proved that if these two wedge powers are different, P and Q, then this is 0. And so really, even if I varied those exponents independently, I get a univariate polynomial, and that thing is G. And in our focusing on the top coefficient, let's suppose the matroid is connected, call its rank R. Well, okay, then the top coefficient is this Euler characteristic with a sign, and using the exact sequence that relates S and Q, we can change this wedge of S to another wedge of Q dual, and this is the perspective in which we're going to look at it. So we have this Euler characteristic to evaluate, an alternating sum of, at least if there are literal vector bundles, then this Euler characteristic is an alternating sum of dimensions of cohomologies of this tensor of wedge products of Q duals. And what we show is that exactly one of the contributions to this Euler characteristic is non-zero. It is in an odd degree, and so with that negative sign out front, omega comes out being positive. That's how the numerics works in the connected case. I won't talk about the disconnected case here. It's just different numerics. Okay, that's the representable thing. I've written similarly for arbitrary M. Well, for arbitrary M, I don't know how to make sense of this vector bundle cohomology directly. So what we do for not necessarily representable matroids is move to the setting of simplicial complexes, Stanley-Reisner theory, and encode these homological numbers in terms of homological information about the simplicial complex. So here is the big strategy. So what I've said is more or less what's on the slide, except for the surprise that where before I had Q dual of M, some wedge power, tensor Q dual of M, some wedge power. Now I've taken two different matroids, M1 and M2 on the same ground set N, and I'm tensoring a wedge power of one with the wedge power of the other. Why would I do that? It's not motivated by anything in the setup I've said so far, but one way to motivate this is to say that the proof techniques we're using draw heavily on a paper, the paper of Ardila and Boocher, 2016, where they look at the inverse linear space, what's now called the matroid Schubert variety. And that paper is an instance of our setup where the two matroids are different. In particular, the second matroid is U1n. So I'll go through their paper, at least the bits of it we're using on the next 3 slides, to show how we're generalizing it. But really, the natural setting to work in, it has emerged, is to work with 2 different matroids. There is a reasonable way to define an omega invariant for 2 matroids in terms of computations in the Bermuda-Hilbert variety, its cohomology, like this. And so we're going to do the proof in that generality. And here is basically what we do. Starting with the representable case, well, I want some Stanley-Reisner ideal. A good way to get that is as the initial ideal of something else. And this is how I have the representation. I have the matroid tautological bundles. I can use them to build some variety. We'll call it Y of the 2 linear spaces that are the representations. And take its ideal, get some initial ideal. Its ideal, a piece of technology, Cartwright-Sturmfels ideals developed by Conca, de Negri, and Gorla in a 2020 paper. These are some Cartwright-Sturmfels and Cartwright-Sturmfels star are some nice classes of ideals which behave well under generic initial ideal, preserving some multigrading. So not truly generic initial ideal, but generic subject to preserving some multigrading. So it turns out that our variety has this property, and one of the consequences is that if we take the initial degeneration we want, the free resolution, the shape of the free resolution doesn't change. In principle, it could jump when we take an initial ideal. Here it doesn't. So then, the game is to give a, in the representable case, we have this tool set Weymann's geometric method that relates homological information of this ideal to the homology of the vector bundles we've started with and their wedge powers. So we can take the free resolution and show that Betti numbers in that free resolution encode the Euler characteristic that we're looking for. As for the non-representative case, well, we need to pull out the combinatorics in this representable thing. So it turns out that there is some matroid and some generalization of external activity that you can use to describe the combinatorics of this initial ideal. So we set that up for an arbitrary pair of matroids, and then have to show that the thing we built for an arbitrary pair of matroids still encodes some counterpart of the Euler characteristic. Well, still encodes the Euler characteristic for the matroid tautological vector bundles that we want, and still encodes some counterpart of the cohomologies. We do this by bivaluativity, which is to valuativity as bilinearity as to linearity, since now we have 2 arguments. It's the obvious 2-argument version of valuation, which you'd think of if you tried to write one down yourself. All right. So, yes, let's talk about the bits of the Ardila-Boocher paper that we're generalizing. So, what I've written down here is the definition of fundamental circuit of a matroid. The fundamental circuit is the unique of a basis and an element, is the unique circuit contained in the union of that basis and that element. It always contains the element I. And if I've found this, I can ask whether my element I was the minimal thing in this distinguished fundamental circuit or not. And the answer to that question is the classical notion of matroid activity for the external case. An element that doesn't lie in my basis is either externally active or passive, and we say it's externally active if it is the minimum of its fundamental circuit. So this is, you can present the top polynomial as a sum of reactivity and so forth. This is a very classical notion, as matroid theory goes. The way that Ardila and Boocher encode these matroid external activity data is in a simplicial complex. So I've given a definition plus theorem here, and the content is I'm describing a simplicial complex in two ways. I'm telling you which sets are its facets, and I'm telling you which sets are its minimal non-faces. And if I told you either of those collections of sets, it would be enough to completely prescribe a simplicial complex. And so the theorem is that the two of them agree to find the same simplicial complex. In this case, what you can do, I can make a simplicial complex where the facets come from coloring the bases B of M. I'll say coloring meaning assigning X or Y to each element. And okay, I'm sort of over-coloring. Really, I give the elements of the basis two colors, and I give each non-element of the basis one color according to whether it's externally active or externally passive or not. So that is a way of encoding this, a basis together with the externally active or passive status of every non-element. I get a face of this simplicial complex, a facet. So I can do that by labeling the bases. On the other hand, I could take the circuits and just label them according to the activity, according to which element of the minimum. Label the minimum with an X and color all the non-minimum elements with Y. And that gives me another subset of x1, xn, y1, yn. And the theorem is that these two things go together, form Alexander dual pair, whatever you have it. The definition makes it not too hard to check that if I have the facet for B, for a basis B, then this coloring on the X's and Y's is exactly what I need so that the non-face for C sub BI misses the facet, isn't a subset of the facet for B, but there is much more to the statement that none of the bases intersect any of the colored circuits this way, and so that is one of their theorems. This duality of sorts between colored bases and colored circuits. All right, that monomial ideal is an initial ideal of a variety. Which variety? Well, what we now call the matroid-Schubert variety. You take your linear space, in the representable case, you take your linear space, you close it up in P1 to the n, and then we move back to the affine setting by taking the n-fold affine cone, just so I can work with an ideal in 2n variables. What is this geometrically? Well, what I've done is if I take a point of my linear space, then I take the matrix, the 2 by n matrix, where the coordinates of that point appear in the first row, all ones appear in the second row, and then I can rescale each column independently because of the n factors of P1. So that's why I have the T1 through Tn here. I have a diagonal n torus action on this 2 by n matrix. And the closure of the space of such matrices is this variety y hat of L. The equations for L, I want to tell you what the ideal of this y of L is. Well, what are the equations for L? The equations of L come from the circuits of a matroid. In this case, it's the dual matroid of the one I said associated to L. But for each circuit of that dual matroid, I get a linear equation that's true of L of minimal support. How do I get the equations for this closure of L in P1 to the n? Well, I just substitute for the variables these ratios x1 over y1 through to xn over yn, and then clear denominators. That gets me a polynomial that vanishes on y of L. But when I clear denominators, which y's I have to introduce is determined by the support of f. And so the support of the polynomial that comes out, the Zn degree of the polynomial that comes out, encodes the support of f, and the minimal generators of this ideal come in that way from circuits. So the ideal of y hat of L knows the circuits of M. The circuits of M are the Zn degrees of its minimal generators. Oh, I didn't say what my gradings are, but I put them here on this slide. There are sort of 4 natural gradings on this polynomial ring: the Z grading, the Z squared, the Zn, and the Z2n gradings. Our ideals of interest will mostly be homogeneous in the Z squared and the Zn gradings. So, well, I described this variety, y of L. You take its ideal, and the theorem I've been hinting is that if you take its initial ideal, that's a square-free monomial ideal, and it is the Stanley-Reisner ideal of the simplicial complex I said before.
Can I interrupt, Alex, with a question from the chat?
Yes.
Maybe Cynthia will just repeat.
Oh yeah, Alex, on the matrix on the slide before, you were saying that the matrix was 2 by n.
Yeah.
I see Andy is answering.
Right. And yes. So I don't take the whole V. I take one element of L. So it's not the whole matrix.
Oh,
it's
I see.
one thing. You know.
Yeah. Okay.
Yeah.
Great.
Right.
Thanks.
Sorry, I wasn't watching the chat. Thank you, Andy. So yes. All right. So this is the combinatorial apparatus that we want to generalize. How do we do it? Well, before we took a linear space L, we took, as Cynthia just asked, one element of that linear space, put it in a 2 by n matrix, filled out the second row with ones, and then acted by a diagonal matrix on the left, on the right, sorry. Well, now I want to do the same thing, but take 2 different linear spaces, pick an arbitrary single vector from the first, put it in the first row, pick an arbitrary single vector from the second, put it in the second row, and then act by a diagonal matrix on the right. So you can think of what we were doing before as just, I take the all ones vector for the second row all the time. The torus action allows me to take any multiple of the all ones vector. That doesn't make a difference. So what we were doing before is the case where this second linear space with the span of the all ones vector. So we always basically just take the all ones vector and an element of L1. Now we'll use 2 different linear spaces, take an element of each. And the orbit closure of the space of matrices you get by taking an element of each and acting with some diagonal matrix. In terms of the vector bundles, what we're doing is we are taking the direct sum of 2 tautological subbundles, because these U's and V's are elements of fibers or stalks of these tautological subbundles, and then projecting away from the base, meaning, taking any point in Xn in the big torus in Xn, these are our T's, or it turns out Xn has the right combinatorics to compactify this thing. And then we look at all 2 by n matrices you can obtain for some choice of T's, that's the base, and some choice of U's and V's, that's the points in the fiber. So you have this map embedding SL into Cn and then projecting away. So SL1 plus SL2 maps to Cn plus Cn. If I call that pi, then the variety we're looking at is pi of this sum of 2 subbundles. Now, using this tool set with Weymann's geometric method, if the dimensions are right, if y is the largest dimension possible, which is this right, dimension L1 for the choice of U, dimension L2 for the choice of V, n minus 1 for the diagonal matrix, because if I act by scalar multiple identity, that will just scale my choices vector from L1 and L2, so I lose a degree of freedom that way. But aside from that degree of freedom, if the thing is as large dimension as possible, which is this, then you get that the pi on the previous slide is actually birational. And using a bunch of technology from my previous paper with Andy about Binglin-Lee tells you a multiplicity freeness result, and Brion gives you rational singularities, and then you pull it along through the ring of sections of vector bundles. There's a bunch of technology like that that says this thing can have Weymann's geometric method for syzygies run on it. And the upshot is that if you take a minimal free resolution of this thing, then actually it has the homologies of all of these vector bundles inside it, of the wedges of, well, okay, I wrote wedge of Q1, tensor wedge of Q2 before, but that's a summand of wedge of the direct sum of the two Qs. So this is the relationship between the resolution of our simplicial complex Stanley-Reisner ideal and the tautological bundles. Okay, let's get back to the combinatorics. On the Ardila-Boocher work, we just had this coloring that came from external activity of the circuits of the matroid of L. Now we've got two matroids. What do we color? Not just the circuits of one or the other. It turns out we have to color the circuits of some bigger matroid that we build from them. This is, I guess, the key combinatorial tool. We call it the diagonal Dilworth truncation because it's like the diagonal bit of Dilworth's original Dilworth truncation from 1944, which was if I've got a geometric lattice and I want to knock out the rank 1 elements and make a new matroid whose atoms, whose elements are the rank 2 things in my original matroid, well, the Dilworth truncation is a way to complete that bottom truncated lattice back up to a geometric lattice. So the definition I've given here is probably inscrutable. This is like Jack Edmonds style, what do they call it, beta zero functions and stuff. But what you should think is the representable case. So what's going on? If I represent my two matroids by vector configurations, so I have some subspace V1 in which M1 is represented by some vectors. I have some subspace V2 in which M2 is represented by some vectors, the same number of vectors because they have the same ground set. Then what I'm doing is I am taking all lines between, right, I take the direct sum, that's what this picture is meant to say. I take the joins, I take the lines between the point representing the matroid on one side and the point representing the matroid on the other side. And then I take a generic hyperplane section in the direct sum. The generic hyperplane section cuts my lines back down to points. So now I have a point configuration in this hyperplane section. And that is the representation of this D, diagonal Dilworth truncation. So
Is this the deletion of the Dilworth truncation of the usual direct, like the direct sum?
Yes, if I take the Dilworth truncation of the direct sum in the way that, you know, would give you parallel elements for parallel pairs and such, and then I just delete everything that's not on the diagonal. That's this thing. That's right. Well, what we really care about are the independent sets of this thing and the circuits of this thing, the bases of the circuits, because we want to make the counterpart of this simplicial complex. So I guess you can characterize the bases in terms of something almost like matroid union, A set is independent if, whenever I add an element, even a duplicate of an element that was already there, I can multi-set partition it into independent sets. The circuits, you have a nice description as well. The circuits are the minimal non-empty sets, so that if you add up their ranks in the two input matroid, they sum to the size of the circuit. This second characterization in particular we'll use when we make our new Stanley-Reasoner ideal. So, okay, we have these two characterizations of D. And like before, I want to make a simplicial complex where the bases and the circuits with a suitable coloring are in some dual role, generalizing Ardila and Boocher. So here's what we do. You can take any weight order on our 2n variables. And now, well, when we colored the circuits, every circuit is partitionable into independent set in M1 and independent set in M2. That is, that's part of the definition here, right? The size of C is exactly the right size to be an independent set in M1 and an independent set in M2. And it turns out there always exist partitions. So among all these partitions, you can encode the partition as a monomial, and then the weight order on the partitions lets me choose an initial one. If I do this, then I will use this to define a generalized notion of activity, where the things that get an X in the leading monomial, I call those one active, externally one active, and the things that get a Y in the leading monomial, I call those externally two active. And so then we sort of play the same game as before. Maybe I'll jump ahead 2 slides because I want to say that this is a generalization of what Ardila and Boocher are doing. I should keep the definition up. Well, we want to play the same game. There exists a simplicial complex on the set x1 through xn and y1 through yn for these two matroids. And again, we can describe it in 2 dual ways, either by its facets or by its minimal non-faces. To get the facets, you color the bases. Again, pick a basis of, now it's D that is the matroid governing this. Pick a basis of the Dilworth truncation. Put in both x and y for elements of basis, as before. For non-elements, put in either x or y, and the choice is governed by which one appears in this leading monomial. Okay, if those are the facets, then the minimal non-faces are going to come from circuits of the same D, and the circuits, you give only one color to each element, and again, it's the color that is the opposite to the color I gave it above for the fundamental circuit case. So if something was an externally 1 active, I give it an X above, now I'll give it a Y. Externally 2 active, I give it a Y above, now I'll give it an X. So that gives you a colored circuit, which is not a subset of the colored basis B if my circuit is CBI. And again, there's something to check to show that actually these two things describe the same simplicial complex. But the whole Ardila-Boocher machine generalizes nicely, and it really is a generalization. If my second matroid is U1n, okay, what does this mean? I want to partition, well, I should say what D is. I wrote that on a previous slide, but I should write it here. If I want to take the Dilworth truncation of a matroid with U1n, then I just get the first matroid back. So in the Ardila-Boocher case, the D was just the matroid M that you started with. So I'm coloring the circuits of D, that is M. How? Well, I split the circuit into an independent set of M and an independent set of U1n. An independent set of U1n is one element. And then I color them according to which monomial has the greatest weight in some weight ordering. Well, that's just saying the one element of U1n I pick should be the least element if you do it in the weight ordering described here. So indeed, you recover classical activity as a special case of our activity for two matroids. And as before, this simplicial complex is the combinatorial behavior of the orbit closure y hat of two linear spaces I described before. You do this thing with the projection away from the base of the sum of two tautological bundles, take an initial ideal with respect to any term order of your choosing, and you get a square free initial ideal, which can be described by this external activity complex for this Dilworth truncation. Okay. So the last step in the proof outline was to argue that due to some bivaluativity, the homological information that you compute from this simplicial complex is bivaluative for all matroids, and so it matches the Euler characteristic and the homological information from the vector bundles, which are also bivaluative. So I'm not going to do this in depth, but there's some very nice combinatorics of it. And when I gave a version of this talk for David Speyer's seminar, David said, oh, along with your title and abstract, send me a picture, send me an image. We advertise our talks with an image. So I prepared him, took some time to prepare him a nice SVG animation. And then he came back to me and said, oh, our website, our server doesn't understand that SVG is an image type. Too bad. But I wanted to use that image. So I wanted to say what it is in the talk. So I'll briefly say how we prove bivaluativity for the homological information about this simplicial complex that we need. It comes from the fan displacement rule on the Chern classes of the tautological quotient bundle. So these are described very explicitly in the paper of Berget Eur Spink Tseng. They come from taking the Bergman fan. The top Chern class of Q is the Bergman fan of M. And if I want to take a lower Chern class, say the Chern class which is I below the top, then what I do is I take I of the coordinates of a point in the Bergman fan, and I can make them larger, anything I like. That is what I've written in this proposition here. So I could think of by coloring the elements, black for the elements, which I haven't increased in this way, so that still take the value they do in the Bergman fan. So this is encoded by a chain of flats. And white for the elements that no longer correspond to their place in the Bergman fan. Well, if you do this, you can, you have a formula in the cohomology of the tridehedral variety relating the total Chern polynomials of these Qs to the omega invariant. I showed that briefly on a previous slide. But if you use the fan displacement rule to generate them, and the displacement is your arbitrary weight vector W, you actually get a very concrete description of the simplicial complex. The simplicial complex is the set, okay, up to including lower faces, which might not show up. The simplicial complex is the set of, look at the points which are colored black for the first Chern class, give them X's. Look at the points which are colored black for the second Chern class, give them Y's. Take that, put that as a face in your simplicial complex. It is beautifully direct how this relationship works. And so I wanted to show you the little animation I made. Okay, I probably have to be in click mode. Oh, I don't think I can click on this. So, well, let's just open it up in another viewer. So I can click on this. This is just a representation of moving around inside the intersection of two of these Chern classes for the affine geometry of rank 2 over F3. And each of the times that this animation pauses for a second, it is a point corresponding to one of the bases of D, and I am moving around between them through the one-dimensional locus of these intersections of Chern classes, which correspond to codimension 1 faces in D. And I'm not giving a proper explanation here. I'm happy to take real questions about this in the question period, but just I made this lovely animation and I couldn't use it in my advertisement, so I wanted to get something of it. So isn't it pretty? All right. Well. So once you do that, you can present this Euler characteristic, or sorry, you can present the K polynomial, which I called the Hilbert function here, of the Stanley reason ideal, which we're looking at using sum over compactly supported Euler characteristics of certain open cells in the intersection of these two fans, and that gives you the bivaluativity we want. I'm aware I've said too little here. I need to wrap up, so I'll just say, why haven't Andy and I finished writing this up yet? Well, because there's one obvious thing we want to do that is like tantalizingly lying outside our grasp so far, but it should be possible, which is, well, the omega invariant is positive. It should count something. What does it count? Well, we have a conjecture what it counts. Just like the beta invariant of a matroid at the other end of G counts bases of M with internal activity 0 and external activity 1. That is the activity formulation of the top polynomial. It looks like omega is counting bases of this Dilworth truncation of M and M with still normal internal activity 0, but this new generalized external activity 1. So numerically, that seems to be the case. You know, there are some things we are trying to prove that this combinatorial interpretation is indeed true, but either we'll get it and write this up in the paper, or we'll have to leave that as an open question for now. And with that, I'll stop. Thank you.
Thanks, Alex. Questions? Feel free to just unmute, shout them out.
I'll ask one. Alex, somewhere back about the middle of the talk, you did a wedge I of the tautological quotient bundle and tensored with a wedge J of the tautological quotient bundle. I don't remember. I have something right about, yeah, right there. So of course, I guess Wayman's method applies more generally. These could be, you know, various Schur functors of both the quotient or the sub bundle. Did you guys mess around? I mean, obviously, you're trying to do one specific thing, but I'm curious if what you get for other Schur functors here, or if you ever messed around with any of the other Schur functors of that form, because this is just one specific dude or dudette.
That's right. Yeah, people have messed around with this at the Burrs meeting on matroids and this kind of thing in March of last year. This was something lots of people were playing around with. I know Matt has played around with lots of these things and interpreted them as rings of sections. Chris Eur wrote a nice paper on wedges and symmetric powers of these various tautological bundles, computing the cohomology, and he tried for Schur functors, and the kind of deletion contraction recurrence he was using from Grauert's theorem, the apparatus was just too complicated to carry them through. Andy and I have certainly been thinking about Schur functors. I mean, we conjecture that there should be some broad positivity that corresponds to like Fulton's positivity for Schur functors of these tautological bundles, but I don't think we know how to get at that yet. Maybe Andy has more ideas, but
well, the one thing that we did prove in the older paper was that if you apply any Schur functor to a tautological bundle, then there's no higher cohomology.
Right.
And Yeah, so but we weren't able to do anything for the non, I mean, this is our first attempt at doing like the non-positive bundles.
So if I
Right.
take, sorry.
Go ahead.
So did you say that if I take this y hat of L1, L2 and I quotient by the C star to the N, then I get
Mhm.
something that's a 0 and multi-degree?
Yeah.
Yeah.
What what computation on involving tautological bundles, like what intersection theory computation does that correspond to?
That's something that kind of confuses me because like for the tautological bundles, like it sort of should correspond to just multiplying like the Chern class of Q of M1 times a Chern class of Q of M2. But you're remembering like different information. Like that's computing bases of D by their external activity. And then the multi-degree that you're talking about is just like the basis and numerator for D.
Right.
Sorry, Alex, I just stole your thunder.
Yeah, no. You right. You said it more fluently than I would have been able to. There is some funny non-positive linear combinations of these products of individual Turing classes that count things related to D. So it's this is what's giving us trouble in the enumerative interpretation, that it's not just directly one product of Turing classes is one enumerative invariant of the D. But
And this
go ahead.
this quotient is it's not literally the Ardila Boocher variety for D, right? It's like some other thing with the same multi-degree. Is that?
Yeah, with the same n-graded multi-degree, different 2 n-graded multi-degree.
Uh-huh.
I wonder if you could clarify what you were missing in the question of what does omega of M actually count? I didn't quite get that.
I mean, I guess a proof technique. I mean, if we could prove shellability of suitable links, the ones that come up in Hochster's formula of this simplicial complex, then that would do it. That's evaded us. If we could, do the kind of thing we were just talking about and relate internal activity to any of the intersection theory computations that I breezed through in the last section of my talk, that would be likely to give it to us. But seems like there's just one piece of technology that we haven't quite grasped yet.
Is this belief only for connected matroids?
What happens in the disconnected case here?
You truncate one factor down.
Oh, that's right. Yeah. Well, right. So, yes, I leave one M alone and I replace the other M with truncating as many times as I need to make D connected. And then we say something like this.
Yes, so to elaborate on your question, Graham, the omega of M should be it's the dimension of like some homology group of some link inside this external activity complex. And so, what we want to do is, I mean, the best way to prove a formula for it is to compute a shelling for the complex, and then it's going to be the number of like homology facets in that shelling.
You need the link to be shellable or just
It's
wedge of spheres?
we already showed that well, yes, if you have a shellable complex, then all the links are shellable.
I see.
The problem is what the homology faces are. We'd like to say these particular ones are the ones contributing.
Well, thanks very much for sharing all these new ideas, and I hope we get to hear another talk about this again soon. Let's give Alex another round of applause, and look forward to seeing you all again in a month for Cynthia Vincent's talk.
Thanks again.